Hello, in this lecture we'll answer two questions. In the first question, we find out the area of this green shape using two different methods. And in the second question, we find out the radius of this semicircle that is inscribed by this rectangle ABCD. So we'll start with the first question. In the drawing, we have rectangle ABCD. Side AB of rectangle ABCD equals to 4 units in its length. Side A equals to 1 unit in its length. And inside this rectangle ABCD, we have this green shape. The green shape is actually a triangle. So we have to find out the area of this green triangle BEC. We also know that this is angle BEC that equals to 45 degrees in size. Again, our task is to find out the area of this green shape, that is the green triangle BEC. So first of all, ABCD is a rectangle, therefore all those four angles are right angles. We define the length of this line segment ED as x. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB equals to the opposite side DC, but AB is 3. Therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the sum rule, in the same rectangle ABCD, side AD must be equal to the opposite side BC. But AD's total is x plus 1, therefore the opposite side BC must be also equal to x plus 1 units in its length. In the next step, we will do a construction. That is to say, from this point E, we will draw perpendicular on BC. Again, from point E, we will draw perpendicular on BC. So here, this angle equals to 90 degrees in size. This angle also equals to 90 degrees in size according to our construction. We define the touching point of the perpendicular from point E and BC. This point is point M. We're doing this construction, we're going to do the small quadrilateral AE and B. Inside this small quadrilateral AE and B, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, total must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in size. So in the upper quadrilateral AB and B we have 4 degrees, and therefore can relate to this quadrilateral AB and B is right again. But you also know that the opposite sides of a rectangle are equal to each other. So in the upper small rectangle A, B, and E, side AB must be equal to the opposite side EM. We define the length of the perpendicular EM as H. Then again, in rectangle ABEM, Side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 3 units in its length. EB equals to EM equals to 3, so EM equals to H, and therefore H equals to 3. In the next step, we will implement the Pythagoras theorem on this upper right triangle ABE. In this upper right triangle ABE, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a function for Pythagoras theorem. So in this upper right triangle ABE, EB squared, that is the square of the hypotenuse, equals to AB squared plus AE squared. Okay, again, in this upper right triangle AEB, according to the Pythagoras theorem, EB squared, that is the square of the hypotenuse, equals to AB squared plus AE squared. EB is the missing hypotenuse, so electricity, so it is EB squared equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9. Plus AE squared. AE is 1, therefore A squared is 1 squared, that is 1. So in total, if you know that EB squared equals to 9 plus 1, that is 10. So EB squared equals to 10. Here we take out of this equation, and having get that the missing hypotenuse EB equal to the square root of 10 units in its length. This is the missing hypotenuse EB that equals to the square root of 10 units in its length. In the next step, we will implement the Pythagoras theorem on this right lower triangle ADC. Here by PT is the function for Pythagoras theorem. This right triangle ADC, according to the Pythagoras theorem, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. And again, this right lower triangle ADC, according to the Pythagoras theorem, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. EC is the missing hypotenuse, so we leave it as it is, so it is EC square equals to ED square. ED is x, therefore ED square is x square. Plus DC square. DC is 3, therefore DC square is 3 squared, that is 9. So in total, we should know that EC square equals to x square plus 9. Here we will take out of this equation. If I get the missing hypotenuse EC, or the right triangle DC, is equal to the square root of x square plus 9. Units in its length. This is the missing hypotenuse EC, is equal to the square root of x square plus 9 units in its length. In the next step, we calculate the area of this green triangle ABC, that is the area of the green shape, by using two different methods. And then we get the question 3 that says that the area of this green triangle ABC according to the first method of calculation must be equal to the area of the same green triangle ABC according to the second method of calculation. We know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of the green triangle ABC must be equal to the base of the triangle times the height to the base over 2. So we choose the base of this green triangle ABC as BC, so the base is BC times the height. The height is h because it rests on the base with the base BC. So the height is h over 2. BC is x plus 1. Times the height edge is 3 over 2. So if you found out that the area of the green triangle ABC according to the first method of calculation, is equal to 3 times x plus 1 over 2 square units inside. In the next step, we calculate the area of this green triangle ABC in a different way. This is triangle ABC that could be any triangle. You know that side AB equals to a unit in itself, side AC of this triangle ABC equals to B units in itself, and the angle between side AB and side AC is theta. The area of this triangle ABC that could be any triangle equals to A times B times sinus theta over 2. So again, the area of this triangle, the area of this triangle ABC is called very triangle because the multiplication of those two sides by each other times the angle between times sinus the angle between the two sides over 2. So the area of this triangle ABC equals to A times B times sinus theta over 2. So we're going to implement the new rule in our drawing. So the area of this great triangle ABC, according to the new formula, must be equal to the multiplication of the two sides by each other, that is to say it is EB times AC times sinus 45 degrees over 2. And again, the area of this green triangle EBC, according to the second method of calculation, equals to EB times EC. This is actually the multiplication of the two sides by each other, times sinus the angle between the two sides, that is 45 degrees over 2. This is according to equation 2. According to equation 1, if you want to know that the area of the same green triangle ABC is equal to 3 times x plus 1 over 2 square units in its size. So in the next step, we return the equation 3 that states that the area of the green triangle EBC according to the first method of calculation must be equal to the area of the same green triangle EBC according to the second method of calculation. So the area of the green triangle EBC according to the first method of calculation equals to 3 times x plus 1 over 2 square units in its size. And so it is on here again. The area of the green triangle EBC according to the first method of calculation equals to 3 times x plus 1 over 2 square units in its size. And it must be equal to the area of the same green triangle EBC according to the second method of calculation. The area of the green triangle EBC according to the second method of calculation equals to EB times EC times sinus 45 degrees over 2. And this is the equation 3, we have 3 times x plus 1 over 2. The other side of the equation we have EB times CC times 145 degrees over 2. So here we have 2 on both sides of this equation, so 2 will get cancelled. After cancel 2 in the side of the equation, we have 3 times x plus 1, and it must be equal to EB times CC. Times sinus 45 degrees. So 3 times x plus 1 equals to EB times AC. EB equals to the square root of 10 units in its length. So we substitute EB by square root of 10 times EC. EC equals to the square root of x squared plus 9 units in its length. Times sinus 45 degrees. Sinus 45 degrees is square root of 2 over 2. So according to equation 3, we found out that 3 times x plus 1 equals to the square root of 10 times the square root of 2 is the square root of 20. And we have to multiply it by x square root of x squared plus 9 divided by 2. So to that, we found out that according to equation 3, times x plus 1 equals to the square root of 20 times the square root of x squared plus 9 over 2. Here we substitute 20 inside the root by 4 times 5. And we get that according to equation 3, we have 3 times x plus 1 equals to, again 20 is 4 times 5 times x squared plus 9 the square root of 4 is 2, so we'll take 4 out of the root, so inside the root we'll have to only be 5. So to that, according to equation 3, 3 times x plus 1 equals to, again square root of 4 is 2, so inside the root we'll have to only be 5 times the square root of x squared plus 9 divided by 2. So here we have 2 in the numerator, 2 in the denominator, so 2 get cancelled. So I thought according to equation 3, I should find out that 3 times x plus 1 equals to the square root of 5 times the square root of x squared plus 9. So here we square both sides of this equation. So 3 squared is 9. And we have to square also x plus 1, so it is x plus times x plus 1 squared. Equals to the square root of 5 squared is 5. And the square root of x squared plus 9 squared equals to x squared plus 9. Why? Because the square cancels the root and we left only with x squared plus 9. So to that we should know that 9 times x plus 1 squared equals to 5 times x squared plus 9. Here we will open the brackets on both sides of this equation, equation 3. And get that according to equation 3. And again, we open the brackets on both sides of this equation, equation 3. And get that according to equation 3, we have 9 times x plus 1 squared. X plus 1 squared equals to x squared. Plus 1 squared is 1. Plus 2 times x times 1, that is 2x. And it is equals to 5 times x squared is 5x squared. Plus 5 times 9 is 45. So we should know that 9 times x squared plus 1 plus 2x equals to 5x squared plus 45. Here we open the brackets on this side of this equation, equation 3. Again, according to this equation, equation 3. Here, 9 times x squared is 9x squared. Plus 9 times 5 is 9. Plus 9 times 2x is 18x. Equals to 5x squared plus 45. Here we subtract 5x squared for this equation, equation 3. So we have 9x squared minus 5x squared is 4x squared. Plus 18x minus 9 equals to 45. So here we subtract 45 from this equation, equation 3. And again, according to equation 3, we have in this side of the equation we have 4x squared plus 18x and 9 minus 45 is minus 36 equals to 0. Here we will divide this equation 3 by 4. And finally get this according to equation 3. 4x squared over 4 is x squared plus 18x over 4 is 4.5x and minus 36 over 4 is minus 9 equals to 0. 0 over 4 is 0. So into that, we should find out that x squared plus 4.5x minus 9 equals to 0. So this is the quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. A, B, and C are the coefficients of the quadratic equation. Okay, again, A, B, and C are the coefficients of this quadratic equation, and x is the variable that we're looking for. And we will find out the value of x according to the following formula. X equals to minus b plus minus square root of v squared plus 4 times a times c over 2a. Now a specific quadratic equation, that is to say x squared plus 4.5x minus 9 equals to 0. The variable that we are looking for is x. And x is the length of this line segment AD. The coefficient a equals to 1. The coefficient b equals to 4.5. And finally, the coefficient c equals to minus 9. So the only thing that is left to do in order to find out the value of x, that is the length of 970 AD, is just to put the data power specific quadratic equation inside this general formula for x. This way we find out the value of the values of x. Why? Because x might have two solutions. So we do it now and get that x, that is the length of 970 AD, equals to minus b. B is 4.5, therefore minus b is minus 4.5 plus minus square root of b squared. B is 4.5, therefore b squared is 4.5 squared, that is 20.25. 1 4 times a times c. A is 1, so 1 4 times a is 1 4 times 1, that is 4 times c. C is minus 9, therefore 4 times minus 9 is plus 36. Divided by 2a. A is 1, so 4a is 2 times 1, that is 2. So in total, if you want to know that x equals to minus 4.5 plus minus, inside the root we have 20.25 plus 36, that is 56.25 divided by 2. So x equals to minus 4.5 plus minus the square root of 56.25 is 7.5 over 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to minus 4.5 minus 7.5 over 2. Repeat again for the first solution for x. X equals to minus 4.5 minus 7.5 over 2. Minus 4.5 minus 7.5 equals to minus 12, and minus 12 over 2 equals to minus 6. So according to the first solution for x, we'll know that x equals to minus 6 units in its time. But because of the fact that x is the length of this constant ED, so x as a length, it must be a positive number. Therefore x can never be equal to minus 6. X must be a positive number. So we cancel the solution and we will take into account only the other solution for x. X equals to minus 4.5 plus 7.5 over 2. So x equals to minus 4.5 plus 7.5 equals to 3 over 2. So in total, if you know that x equals to 3 halves, then 1.5 units is there. Our task is to find out the area of this green shape. The green shape is actually triangle ABC. So our task is to find out the area of this triangle ABC. So write it down. is again the green shape is triangle ABC, so our test is to find out the area of the green triangle ABC. We know that the area of any triangle equals to the base of the triangle times the height over 2. So we choose the base of this great triangle ABC as BC, and the height is h. And again, the base of the great triangle ABC is BC, and the height is h divided by 2. In total, we should know that the area of the green shape equals to the base BC times the height h over 2. We already found out that BC equals to x plus 1 times the height edge. Edge is 3. Divided by 2. We just right now found out that x equals to 1.5, and therefore x plus 1 is 1.5 plus 1, that is 2.5. So in total, the base BC equals to 2.5 units in there, times 3 over 2. 2.5 times 3 is 7.5, and 7.5 over 2 is 3.75 square units in size. And again, if you want to know that they are that we're looking for this equation, that is the area of this green shape equals to 3.75 square units in size. So we finish with the first method. In the next step, I present to you how to find out the area of this green shape according to the second method. ABCD is right angle, therefore all those four angles are right angles. We define the length of this line 70 ED as x, exactly as we did in the first method. We know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle ABCD, side AB equals to the opposite side DC. But AB is 3, therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the sum rule, in the sum rectangle ABCD, side AD must be equal to the opposite side BC, but AD is x plus 1, therefore the opposite side BC must be also equal to x plus 1 units in its length. construction. This is the shape from point D, we don't perpendicular on BC. So actually, this angle was 90 degrees inside, and this angle also was 90 degrees inside, according to our construction. We define the touching point of the perpendicular from point D inside BC. This point is point M. By doing this construction, we calculate quadrilateral AB, ME. Inside this quadrilateral AB, ME, we have 1, 2, 300 degrees. This focus area must be equal to 90 degrees in size. According to the rule that I mentioned a couple of times, it said that the sum of the angles in a quadrilateral is equal to 360 degrees. So in quadrilateral AEBM, we have 4 degrees, and the focus area to quadrilateral AEBM is 7 degrees. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle ABME, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 3 and it's inside. We define the length of perpendicular EM as h, so EM equals to edge and edge equals to 3. Edge is the height to the base of the great line ABC. Well, for the great 90 degrees with the base BC. In the next step, we focus on this upper right triangle AEB. This upper right triangle AEB, we define this angle AEB as theta. So in this right upper triangle AEB, triangle theta equals to AB over AE. But again, in this upper right triangle AEB, triangle theta equals to AB over AE. AB is 3, AE is 1, so in total triangle theta equals to 3 over 1, that is 3. And again, according to a previous model, we found out that triangle theta equals to 3. We have the trigonometric identity that states that tan 45 degrees plus theta equals to 1 plus tan theta over 1 minus tan theta. And again, we have the trigonometric identity that says that 1 plus tan theta and tan 45 degrees plus theta equals to 1 plus tan theta over 1 minus tan theta. So we'll define this trigonometric identity as equation 2. We already found out that tan theta equals to 3, so we can solve the tan theta in this equation 2 by 3. We do it now we get that tan 45 degrees plus theta equals to 1 plus tan theta, and tan theta is 3, so it is 1 plus 3 over 1 minus tan theta. So it is 1 minus tan theta, that is 3. So if you found out that tan 45 degrees plus theta equals to 1 plus 3 over 1 minus 3. 1 plus 3 is 4, and 1 minus 3, 1 plus 3 is 4, and 1 minus 3 is minus 2. So tan 45 degrees plus theta equals to 4 over minus 2, that is minus 2. So if you found out that according to equation 2, tan 45 degrees plus theta equals to minus 2. This is according to equation 2, and according to equation 1, we already found out that tan theta equals to 3. AD is one side of rectangle ABCD, therefore it is absolutely a straight line. AD is a straight line. So if you focus on the right side of the straight line AD at point E, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So we take as we have the right side of the straight line AD at point E. We have angle theta plus this angle is equal to 45 degrees in size, plus this missing angle, the angle DEC, because again, according to equation rule 3, the sum of the angles on one side of the straight line is equal to 180 degrees. So the sum of the angles on the right side of the straight line AD at point E must be equal to 180 degrees. So which angle we have at the right side of the straight line AD at point T? We have triangles theta 45 degrees and the missing angle DEC. So the sum of those triangles must be equal to 180 degrees according to rule 3. So here we will subtract theta plus 45 degrees from this equation. And finally we get the missing angle DEC equals to 180 degrees minus theta plus 45 degrees. So actually, this is the missing angle DEC. This is equals to 180 degrees minus theta plus 45 degrees. In the next step, we'll focus on this right triangle DEC. On this right lower triangle EDC, tangent 180 degrees on theta plus 45 degrees equals to DC over DE. So, write it down. In the right lower triangle EDC, tangent 180 degrees from theta plus 45 degrees equals to DC or ED. And again, according to equation 3, we should found out that tangent 180 degrees minus theta plus 45 degrees equals to DC over ED. DC is 3 over ED is X. In total, if you found out that according to equation 3, tangent 180 degrees minus theta plus 45 degrees equals to 3 over X. Here another trigonometric identity that states that tangent 180 degrees minus theta equals to minus tangent theta. So according to this trigonometric identity, tangent 180 degrees minus theta equals to minus tangent theta. What is the value of this expression tangent 180 degrees minus theta plus 45 degrees? So according to this trigonometric identity, the value of tangent 180 degrees minus theta plus 45 degrees will be equal to minus tangent theta plus 45 degrees. So we can substitute tangent 180 degrees minus theta plus 45 degrees in this equation 3 by minus tangent theta plus 45 degrees because they are equal to each other according to this trigonometric identity. So we do it now and get it according to equation 3. Again, tangent 180 degrees minus theta plus 45 degrees equals to minus tangent theta minus tangent theta plus 45 degrees of course. According to equation 3, it equals to 3 over x. But according to equation 2, we only found out that tangent 45 degrees plus theta equals to minus 2. So we substitute tangent theta plus 45 degrees in this equation 3 by minus 2. So here we have minus, so I copy the minus here, and we have tangent theta plus 45 degrees equals to minus 2 according to equation 2. So we substitute tangent theta plus 45 degrees by minus 2. So in this side of the equation we have minus 2, that is plus 2, and it equals to 3 over x. Again, minus 2 is plus 2, so 2 equals to 3 over x. Here we will multiply this equation 3 by x. If I get this according to equation 3, 2x equals to 2x equals to 3. Here we divide this equation 3 by 2. And finally we get that x equals to 3 halves, that is 1.5 units. So x equals to 1.5 units in itself. X is enough of this lesson, ED. Our task is to find out the area of this green shape. So what is the area of the green shape? The green shape is actually the green triangle EBC. So our task is to find out the area of this green triangle EBC. we know that the area of every triangle equals to the base of the triangle times the height over 2. We choose the base of this right triangle ABC as BC. The height edge is 3 over 2. BC equals to 1 x plus 1. The height edge equals to 3 divided by 2. So the area of the green shape equals to x plus 1 times 3 over 2. But we already found out that x equals to 1.5, therefore x plus 1 equals to 1.5 then plus 1, that is 2.5. Times the height edge, that is 3 over 2. 2 times 5 times 3 is 7.5, and 7.5 over 2 is equal to 3.75 square size. So in both methods, we can find out that the area that we're looking for in this question, that is the area of this green shape, equals to 3.75 square in size. So we finish with the first question. The next step, I present you with the second question, and we'll solve the second question of this lecture. In this second question, our task is to find out the radius of this semicircle. So, in the drawing, we have a semicircle that is described by this rectangle ABCD. This is the short line side QB, is equals to 1 unit in its length. This is the segment PD, is equals to 2 units in its length. Again, our task is to find out the radius of this semicircle. So first of all, ABCD is right angle, therefore all those four angles are right angles. In the next step, we define the point of tendency of tangent DC with this semicircle. This point is point T. Likewise, we define the point of tendency of tangent BC with this semicircle. This point is point L. We define the center of this semicircle. This point is point O. And finally, we define the radius of this semicircle as x. The next step, we join points O and T together by a straight line. Point O is the center of the semicircle, point T is the point of the semicircle itself, therefore OT is the radius of this semicircle, is equal to x according to our definition. The radius of T is equal to x, the radius of T is drawn to point T, this is the point of tendency DC with this semicircle. And whenever your radius that is drawn to the point of tendency, then tangent DC will be perpendicular to radius TO. If DC is perpendicular to TO, it means that this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside, according to all 1. Likewise, we join points O and L together by a straight line. Point O is the center of the semicircle, point L is the point of the semicircle itself. Therefore, OL is the radius of this semicircle, equals to x. L is the point of tendency obtained BC with this semicircle. The radius OL is equals to x, the radius OL is drawn to point L, that is the point of tendency obtained BC with this semicircle. And whenever your radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule or 1. By doing those constructions, we can have here the lower quadrilateral OLCT. So the lower quadrilateral OLCT, we have 1, 2 periodicals. The sum of periodicals is 230 degrees, so 230 degrees plus the size of this 450 degrees, so that must equal to 360 degrees according to the rule that says the sum of the degrees in a quadrilateral, the sum of the degrees in a quadrilateral is equal to 360 degrees. Therefore, this 450 degrees must be equal to 90 degrees in size. So in quadrilateral OLCT we have 4 degrees. Therefore, can you write quadrilateral OLCT is rectangle according to rule 5. Rule 5 states that the sum of the angles in a quadrilateral, if a quadrilateral is 4 degrees, it must be this rectangle if not a square. So we write quadrilateral OLCT is rectangle because it has 4 degrees. So in rectangle OLCT, side OL must be equal to the opposite side TC, but OL is x, therefore the opposite side TC must be also equal to x units in its line. Likewise, according to the sum rule, in the sum rectangle OLCT, side OT must be equal to the opposite side LC, but OT is x, therefore the opposite side LC must be also equal to x units in its line. So she will know that quadrilateral OLCT is not a rectangle but a square, but because of the fact that all of its sides are equal to each other, each side equals to x. So if you know, this is quadrilateral OLTC, it is a square. In the next step, we will do a construction that is shape from point O, that is the center of the semicircle. We draw perpendicular on AB. So actually, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point M. By doing this construction, we created the upper quadrilateral MBLO. Inside this quadrilateral MBLO, we have 1, 2 third angles. Therefore, this fourth missing angle must be equal to 90 degrees in size. According to the rule that I mentioned a couple of times, it says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in size. So in quadrilateral MBLO we have four right angles, and therefore we can write to this quadrilateral MBLO as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper small rectangle MBLQ, side OL must be equal to the opposite side MB. But OL equals to x, therefore the opposite side MB must be also equal to n units in its length, to x units in its length. What is the length of this missing line side? Line side MQ. MQ equals to MQ equals to MB minus QB. So now, if you hold on the missing line side MQ equals to MB minus QB. And so that if you hold on the MQ equals to M and B. MB is x minus QB. QB is 1, so in total MQ equals to x minus 1 units in its length. In the next step, we will do another construction, that is to say from point O, that is the center of this semicircle, we draw perpendicular on AD. So actually, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside, according to our construction. We define the touching point of the perpendicular from point O and AD. This point is point S. When doing this construction, you can do the upper quadrilateral AMOS. Inside this quadrilateral AMOS, we have 1, 2 parameters. Therefore, this fourth missing must be equal to 90 degrees inside. So quadrilateral the upper quadrangle AMOS we have 4 address, and therefore you can relate to this quadrangle AMOS as a rectangle. By doing this construction, we can get the lower quadrangle OS dt. Inside this lower quadrangle OS dt, we have 1, 2, 3 address, and therefore this 4 pieces must be equal to 90 degrees in size. According to the rule that I mentioned a couple of times, that said that the sum of the areas in any quadrangle is equal to 360 degrees. Therefore, this 4 pieces must be equal to 90 degrees in size. So in quadrangle OS dt we have 4 areas, and therefore we can relate to this quadrangle OS dt as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So the lower rectangle OS dt, side OT must be equal to the opposite side SD. But OT is x, therefore the opposite side SD must be also equal to x units in its length. What is the length of this missing line segment? Line segment SP. SP equals to SD minus PD. But you know, again, SP equals to SD minus PD. So SP equals to SD. SD is x minus PD. PD is 2 according to what is given in the question. So in total, we actually found out that SP equals to x minus 2 units in its length. This is the big angle SOL. The big angle SOL equals to 90 degrees plus 90 degrees, that is 180 degrees. So now we found out that the big angle SOL equals to 180 degrees in its size. And we know that any angle is equal to 180 degrees in its size is defined as a straight line. Therefore, line segment SOL is a straight line. So, if line segment SOL is a straight line, then SL is also a straight line. If not, SL is a straight line. And therefore, this is shape ABLS, that is 1, 2, 4, 1, 2, 3, 4 sides. The upper shape ABLS has 4 sides. And therefore, shape AB and P must be equilateral. The upper shape ABLS, shape ABLS is a quadrilateral. This quadrilateral ABLS, we have 1, 2, 3, 4 right angles. Quadrilateral ABLS is 4 right angles. According to rule 5, any quadrilateral that has 4 right angles must be at least rectangle if not a square. So we relate to quadrilateral ABLS is a rectangle because it has 4 right angles. And again, we should know that this is quadrilateral ABLS. It is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are parallel to each other. So in this upper small rectangle ABLS, side AB must be parallel to the opposite side SL. According to the rule that says that the opposite sides of a rectangle are parallel to each other. Repeat again, side AB is parallel to side SL. This is transversal, again, this is transversal QP. Transversal QP cuts those two parallel sides at those 2 points Q and O. Again, transversal QP cuts those two parallels at those 2 points Q and O. So all the requirements of Rule 10 are satisfied, and therefore we can implement Rule 10 in our drawing. Repeat speaking on Rule 10. According to Rule 10, corresponding angles between parallel lines are equal to each other. In the drawing, we have line A that is parallel to line B. This is the red line C. It is defined as transversal. That is to say, it cuts those two parallel lines at those 2 points. Those 2 angles are both defined as corresponding angles and they are located between the parallel lines A and B. And therefore, they must be equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to this rule, Rule 10. It doesn't matter if you call to those angles as alpha or 1. 1 is not a number, but it is the name of the angle. Okay? Likewise, those 2 angles are also defined as corresponding angles, and they are located between the parallel lines A and B. Therefore, they must be equal to each other in their sizes. So if you define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other in their sizes. Again, 2 is not a number, but the name of the angle. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta according to this rule, Rule 1. Likewise, if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to this rule, Rule 10. So we can definitely implement Rule 10 in our drawing. As I already mentioned before, all the requirements of Rule 10 are satisfied, and therefore we can implement Rule 10 in our drawing. Repeat again. We already found out that Side AB is parallel to the opposite side SL in rectangle AB LS. So AB is parallel to SL. QP is the transversal of this. We have QP is the transversal. That is to say, it cuts those two parallels at those 2 points Q and O. Again, all the requirements of Rule 10 are satisfied, and therefore can implement a Rule 10. Those two angles, they are both defined as corresponding angles, and they are located between the parallels AB and SL, and therefore they must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to Rule 10. The set is corresponding angles between parallels are equal to each other. Those two corresponding angles are located between the parallels AB and SL, and therefore they must be equal to each other and their sizes. So the size of this angle is alpha, and then the size of this angle must be also equal to alpha according to Rule 10, because they are equal to each other according to Rule 10. So in this upper right green triangle MQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Well, because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in the lower green triangle SOP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. According to the sum rule, that said that the sum of the angles in any triangle is equal to 180 degrees. What is the length of line segment OQ? Line segment OQ starts from point O, that is the center of the semicircle, and ends at point Q, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OQ is the radius of this semicircle, is equal to x units in its length. Likewise, OP, this is line segment OP, that starts from point O, that is the center of the semicircle, and ends at point P, that is the point of the semicircle itself. Therefore, OP is also the radius of this semicircle, that is equal to x units in its length. In the next step, we will prove that those two right green triangles can go into each other according to angle side angle rule. So this is the upper green triangle MQO. We have to prove that this upper green triangle MQO can go into this lower right triangle SOP. So what those two green triangles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. This is angle MQO. The right upper green triangle MQO, and this is equal to this angle. This is the angle SOP. In the right lower green triangle SOP. Okay, again, if you found out that angle MQO in the right green upper triangle MQO equals to angle SOP in the right lower green triangle SOP. They are both equal to alpha and therefore they are equal to each other. In addition, those two sides are also equal to each other. They are both the radii of the semicircle equals to x and therefore they are equal to each other. So this is side QO of the upper right green triangle MQO and is equals to this side, that is side OP in the right green lower triangle SOP. Again, side QO and the right upper triangle MQO is equal to side OP in the right lower triangle SOP. They are both the radii of the semicircle equals to x and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So actually, this is angle MOQ. In the right upper green triangle MOQ, and it is equal to this angle, this is actually angle SPO. The right lower green triangle SPO. Because again, if you found out that angle MOQ in the right upper green triangle MQO is equal to angle SPO in the right green lower triangle SPO, they are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you found out that those two green right triangles can go into each other according to angle side and angle rules. So write it down. If you found out that the upper green right triangle MQO congruent, this is the sign of congruent, to the right lower green triangle SOP according to angle side angle rules. Again, if you found out that the upper right green triangle MQO congruent to the lower right green triangle SOP according to angle side angle rule. That is to say, if you found out that those two angles and the side that is included between those two angles, that is side QO, and this upper green right triangle MQO are correspondingly equal to those two angles, and the side that is included between those two angles, that is actually side PO, this green right lower triangle SOP, and therefore those two green right triangles can go into each other according to angle side angle rule. Okay, again, those two angles and the side that is included between those two angles, that is side OQ, this upper green right triangle MQO correspondingly equal to those two angles, and the side that is included between those two angles, that is side PO, and this green right lower triangle SOP. Therefore, those two green right triangles can go into each other according to angle side angle rule. And from the fact that those two green right triangles can go into each other, we will derive that their corresponding sides must be also equal to each other and their lengths. According to the rule that says that the corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore their corresponding sides must be also equal to each other and their lengths. Actually, side MQ of this green triangle MQ is the corresponding side of side SO of this green right lower triangle SOP. Right, those two sides are the corresponding sides because of the fact that those two sides are both located in front of this angle 90 degrees minus alpha, and therefore they are the corresponding sides. So if you found out that MQ equals to SO, those two corresponding sides are equal to each other. That is to say, MQ equals to its corresponding side, side SO. Side MQ of the green upper right triangle MQ equals to side SO of the green upper lower triangle SO. But we already found out that MQ equals to x minus 1, so we can write that MQ equals to x minus 1. And from this equation, x minus 1 equals to MQ equals to SO, we will derive that SO must be also equal to x minus 1 units in its length. So here this is the missing side SO, this is also equal to x minus 1 units in its length. In the next step, we will implement the Badar's theorem on this right green lower triangle, SPO. Here by PT is the abbreviation for Badar's theorem. According to the Badar's theorem, in this green right lower triangle SPO, OP squared, that is the square of the hypotenuse, equals to SO squared plus SP squared. And again, this right triangle SPO, according to the Badar's theorem, OP squared, that is the square of the hypotenuse, equals to SO squared plus SP squared. OP is x, therefore OP squared is x squared, and it equals to SO squared. SO is x minus 1, therefore SO squared is x minus 1 squared plus SP squared. SP is x minus 2, therefore SP squared is x minus 2 squared. So in total, we should find out that x squared equals to x minus 1 squared plus x minus 2 squared. Here we open the brackets on this side of this equation, and we get that x squared equals to x minus 1 squared. X minus 1 squared equals to x squared plus 1 squared, that is 1, plus 2 times x times 1, that is minus 2x, plus x minus 2 squared. X minus 2 squared equals to x squared plus 2 squared, that is 4, minus 2 times x times 2, that is minus 4x. Here we have x squared on both sides of this equation, so x squared will get cancelled. After we cancel x squared, this side of the equation will be left with nothing, that is to say 0. While on the other side of the equation, we have 1 plus 4 is 5. We have minus 2x minus 4x is minus 6x plus x squared. So in total, we should find out that x squared minus 6x plus 5 equals to 0. Repeat again. Also, we find that x squared minus 6x plus 5 equals to 0. This is a quadratic equation, and the general formula for quadratic equation is as follows. Ax squared plus bx plus c equals to 0. In this general formula for quadratic equation, a, b, and C are the coefficients of this quadratic equation. And x is the variable that we're looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared minus 6x plus 5 equals to 0, the variable that we're looking for is x, and x is the radius of the semicircle. The coefficient a equals to 1, the coefficient b equals to minus 6, and finally the coefficient c equals to 5. So actually we have all the data that is needed in order to find out the value of x, that is the radius of the semicircle. The radius of the semicircle. The only thing that is left to do is just to put the data of our specific quadratic equation inside this general formula for x. This way we find out the value of the values of x. So x might have two solutions. So we do it now, we get that x, that is the radius of the semicircle, equals to minus b. b is minus 6, so b is minus 6, that is plus 6, plus minus square root of b squared. b is minus 6, so b squared is minus 6 squared, that is 36, minus 4 times a times c. So it is minus 4 times a is also minus 4 times 1 is minus 4 times c. c is 5, so minus 4 times 5 is minus 20. So inside the root we have 36 minus 20 over 2a. a is 1, so 2a is 2 times 1, that is 2. So today we found out that x, that is the radius of the semicircle, equals to 6 plus minus 36 minus 20 is 16, so inside the root we left only with 16 over 2. So if we found out in total that x equals to 6 plus minus, and the square root of 16 is 4 over 2. Repeat again, if you found out that x equals to 6 plus minus 4 over 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to 6 plus 4 over 2. 6 plus 4 is 10, and 10 over 2 is 5. So if you found out that according to the first solution for x, x that is the radius of the semicircle, equals to 5 units in its length. The radius of this semicircle x equals to 5 units in its length. We have another solution for x. The second solution for x is as follows. X equals to 6 minus 4 over 2. 6 minus 4 is 2, and 2 over 2 is 1. So the second solution for x is that x equals to 1. But actually, this second solution is the correct solution. Why? Because of the fact that we already found out that line 7 SP equals to x minus 2 units in its length. SP equals to x minus 2 units in its length. If x equals to 5, then x minus 2 is 5 minus 2 is 3. So SP definitely can be equal to 3 itself. What happens if x equals to 1? If x equals to 1, then x minus 2 is 1 minus 2, this is minus 1. SP is a left, and SP is a left, it must be a positive number. So due to the contradiction, because there's the possibility that x equals to 1. X can never be equal to 1. Another reason that x can never be equal to 1 is because of the fact that SP equals to x minus 2. So SP is a left, it must be a positive number. That is to say, x minus 2, what is a positive number? X minus 2 must be greater than 0. Here we add 2 to this inequality and get that x must be greater than 2. If x must be greater than 2, x can never be equal to 1, that is less than 2. So we have two reasons that x can never be equal to 1. Therefore, the only solution to this question is that the radius of this semicircle x equals to 5 units in its length. And that is the answer to the second question. So in the next step, I will summarize the lecture, start with the repetition of the solution of the first question, and then we will repeat on the solution of this second question. Our task in the first question was to find out the area of this ring shape. So in the drawing we have a rectangle ABCD. This is line segment AE. This is equals to 1 unit in its length. Side AB of rectangle ABCD equals to 3 units in its length. Inside this rectangle ABCD we have this green shape. The green shape is the green triangle EBC. This is the angle BEC. This is equals to 45 degrees inside. Again, our task is to find out the area of this green shape. That is actually the area of the green triangle BEC. So we start with the first method. So ABCD is a rectangle, therefore all those four angles are right angles. We define the length of this line segment ED as x. So in total, AD equals to x plus 1. You also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 3, therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the sum rule, in the sum rectangle ABCD, side AD must be equal to the opposite side BC. But AD is x plus 1, therefore the opposite side BC must be also equal to x plus 1 units in its length. In the next step, we did the construction, that is to say, from point E, we draw perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point E and BC, this point is point M. But during this construction, we created the upper quadrilateral AB and E. Inside this upper quadrilateral AB and E, we have 1, 2, 3 arteries. The sum of 3 arteries is 270 degrees, so 270 degrees plus the size of this 4th angle. In total, they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4th angle must be equal to 90 degrees in its size. So in quadrilateral AB and B, we have 4 arteries. Therefore, we can write quadrilateral AB and B 3 arteries. But you also know that the opposite sides of a rectangle are equal to each other. So in the upper small rectangle AB and E, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 3 units in its length. We define the length of perpendicular EM as h, so EM equals to h and h equals to 3. In the next step, we implemented the quadrilateral theorem on this upper right triangle AEB. According to the quadrilateral theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So in this right triangle ABE, BE squared, that is the square of the hypotenuse, equals to AB squared plus AE squared. This again, this upper right triangle ABE, according to the quadrilateral theorem, BE squared equals to AB squared plus AE squared. BE is the missing hypotenuse, so we leave this it is, so it is BE squared equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus A squared. A is 1, so A squared is 1 squared, that is 1. So in total, we actually found out that EB squared equals to 9 plus 1, that is 10. EB squared equals to 10. Here we took out all those equations, and we found out that the missing hypotenuse EB equals to the square root of 10 units in its length. This is the missing hypotenuse EB, this is equals to the square root of 10 units in its length. The next step, we implemented the quadrilateral theorem on this ring, the right lower triangle EDC. According to the quadrilateral theorem, in this ring, right lower triangle EDC, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. And then this right lower triangle EDC, according to the quadrilateral theorem, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. EC is the missing hypotenuse, so leave it as it is, so it is EC squared equals to ED squared. ED is x, therefore ED squared is x squared plus DC squared. DC is 3, therefore DC squared is 3 squared, that is 9. So in total, we should know that EC squared equals to x squared plus 9. Here we took out all the equations, and we found out that the missing hypotenuse EC equals to the square root of x squared plus 9 units in its length. This is the hypotenuse EC, is equals to the square root of x squared plus 9 units in its length. The next step, we focus on this green right triangle EBC. Now we calculated the area of this green triangle EBC by doing 2 different methods. And then we created a equation that said that the area of this green triangle EBC according to the first method must be equal to the area of this green right triangle EBC according to the second method of calculation. In the first method of calculation, the area of any triangle equals to the base of the triangle times the height over 2. So we choose the base of this green triangle EBC as BC, the height is edge over 2. So the area of this green triangle EBC according to the first method of calculation equals to the base times the height over 2. The base is BC, the height is edge over 2. So the area of the green triangle BC according to the first method of calculation equals to the base BC times the height edge over 2. BC is x plus 1, edge is 3. And again, BC is x plus 1, edge is 3, so in total the area of the given triangle BC according to the first method of calculation equals to x plus 1 times 3 over 2. Again, the area of the given triangle ABC according to the first method of calculation equals to 3 times x plus 1 over 2. In the next step, we calculated the area of this given triangle ABC according to the second method of calculation. This is triangle ABC that could be in a triangle. Side AB of triangle ABC equals to A units in itself. Side AC equals to B units in itself. This is angle third now. That is the angle between those two sides A and B. The area of this triangle ABC that could be in any triangle equals to the multiplication the two sides by each other, that is to say A times B, times sum of the angle between those two sides, that is theta over 2. Repeat again, the area of this triangle ABC that could be any triangle equals to A times B times sum of theta over 2. So we use the new formula in order to calculate the area of this given triangle, triangle BEC. According to the new formula, the area of this given triangle BEC equals to the multiplication of those two sides by each other, that is to say it is BE times EC times sum of the angle between those two sides, that is 45 degrees over 2. So again, we should order that according to the second method of calculation, the area of this given triangle ABC equals to the multiplication of the two sides by each other, that is to say it is EB times EC times sum of the angle between the two sides, that is 45 degrees over 2. This is according to equation 2, and according to equation 1, we should find out that the area of the same given triangle EBC equals to 3 times x plus 1 over 2. In the next step, we created equation 3 that said that the area of the given triangle EBC according to the first method of calculation must be equal to the area of the same given triangle EBC according to the second method of calculation. According to the first method of calculation, the area of the given triangle EBC equals to 3 times x plus 1 over 2. And it must be equal to the area of the same given triangle ABC according to the second method of calculation. So according to the second method of calculation, the area of the given triangle ABC equals to the multiplication of the two sides by each other, that is to say it is EB times AC times 45 degrees over 2. Here we have 2 on both sides of this equation, so 2 will get cancelled, after cancel 2, and left only this side of the equation we left with 3 times x plus 1. In the other side of the equation we left with AB times EC times 45 degrees. 2 is cancelled. So here we have 3 times x plus 1 equals to EB square root of 10 times EC square root of x squared plus 9 times sinus 45 degrees. Sinus 45 degrees equals to square root of 2 over 2. Here we have square root of 10 times square root of 2 is square root of 20. So if you found out that 3 times x plus 1 equals to the square root of 20 times square root of x squared plus 9 over 2. We substitute 20 by 4 times 5. So 3 times x plus 1 equals to the square root of 4 times 5 times the square root of x squared plus 9. The square root of 4 is 2, so inside the root we left only with 5. So in total, if you found out that 3 times x plus 1 equals to 2 and times square root of 5 times x squared times the square root of x squared plus 9 divided by 2. We have 2 in the numerator, 2 in the denominator, so 2 gets cancelled, so 2 cancels 2. If you found out that 3 times x plus 1 equals to the square root of 5 times the square root of x squared plus 9. Here we squared both sides of this equation 3. If I found out that 3 squared is 9, and we have to square also this expression, so it is x plus 1 squared. And is equals to the square root of 5 squared is 5, and the square root of x squared plus 9 squared equals to x squared plus 9, well, because of the fact that the square cancels the root, and we have only with x squared plus 9. So in total, if you want that according to equation 3, x plus 1 squared equals to 5 times x squared plus 9. We open the brackets on both sides of this equation. If I found out that according to equation 3, we have 9 times x plus 1 squared. X plus 1 squared equals to x squared, plus 1 squared is 1, plus 2 times x times 1, that is 2x, and this is equals to 5 times x squared is 5x squared, and 5 times 9 is 45. We open the bracket on this side of the equation here, and find out that 9 times x squared is 9x squared, plus 9 times 1 is 9, and plus 2 times 9 times 2x is 18x, and it's equals to 5x squared plus 45. Here subtract 5x squared from this equation, so 9x squared minus 5x squared is 4x squared plus 18x plus 9 equals to 5x squared minus 5x squared is 0, so we left only with 45 in this side of this equation 3. Here subtract 45 from this equation, so here we left with 0, and on the other side of the equation we have 4x squared plus 18x, and 9 minus 45 is minus 46. So in total we should know that 4x squared plus 18x minus 46 is equals to 0. Here we divided this equation 3 by 4, and find that 4x squared over 4 is x squared, plus 18x over 4 is 4.5x, and minus 46 over 4 is minus 9, and 0 over 4 is 0. So in total we should know that x squared minus 4.5x minus 9 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus 4.5x minus 9 equals to 0. The variable that we are looking for is x, and x is the length of this line segment ED. The coefficient a equals to 1, the coefficient b equals to 4.5, and the coefficient c equals to minus 9. So the only thing that is left to do in order to find out the value of x that is the length of line segment ED is just to put the data of our specific quadratic equation inside this general formula for x, and this way we find out the value of the values of x, because x might have two solutions. So we did it, and we should know that x equals to minus b. b is 4.5, therefore minus b is minus 4.5, plus minus 4 to b squared minus 4 times a times c. So b is 4.5, therefore b squared is 4.5 squared, that is 20.25, minus 4 times a times c, so it is minus 4 times a is also minus 4, a is also minus 4 times a is minus 4 times c, c is minus 9, therefore minus 4 times a, c is minus 4 times minus 9, that is plus 36. So inside the root we have 20.25 plus 36 over 2a. Is also 2a is 2 times 1, that is 2. So today we found out that x equals to minus 4.5 plus minus square root of 20 plus 25 plus 36 divided by 2. 20.25 plus 36 equals to 56.25 over 2. So in total inside the root we have 56.25, and it was to 7.5. So in total we should find that x equals to minus 4.5 plus minus, and inside the root we have 56.25, that is 7.5. So in total we should find out that x equals to minus 4.5 plus minus 7.5 over 2. So here we have two solutions that are possible for x. The first solution for x is as follows: x is the length of line segment ED. The first solution for x is as follows: x equals to minus 4.5 minus 7.5 over 2. Minus 4.5 minus 7.5 is minus 12, and minus 12 over 2 is minus 6. So we found out that x equals to minus 6, but x can never be equal to minus 6, but why? Because of the fact that x is the length of this line segment ED. So x is the length, it must be a positive number. Therefore, the first solution for x is incorrect solution. We have another solution that is possible for x. The second solution for x is as follows. X equals to minus 4.5 plus 7.5 over 2. Minus 4.5 plus 7.5 is 3, and 3 over 2 is 1.5. So in total, if you found out that x equals to 1.5 units instead. Our task is to find out the area of this green shape. The green shape is actually the green triangle ABC. Again, our task is to find out the green shape, and the green shape is the green triangle ABC. Therefore, our task is to find out the area of the green triangle ABC. The area of the triangle equals to the base of the triangle times the height over 2. Choose the base of the green triangle BC is BC, the height is edge over 2. And again, the base is BC, the height is edge over 2. BC is x plus 1, and edge is 3. Again, BC is x plus 1, edge is 3 divided by 2. X is 1.5, therefore x plus 1 is 1.5 plus 1, that is 2.5. So in total, the base BC is 2.5 times the height edge, that is 3 over 2. 2.5 times 3 is 7.5, and 7.5 over 2 is equal to 3.75 units in size. So in both methods, if you found out that the area that we're looking for in this equation, that is the area of this green shape, equals to 3.75 square units in size. So we finished to repeat on the first question. The next time we repeat on the solution of the second question. Actually, we repeated on the solution of the first method. In the next step, repeat the solution of the second method. ABCD is a rectangle, and therefore all those four angles are right angles. And we define now AD is x. We know that, so AD in total equals to x plus 1. The opposite sides of a rectangle are equal to each other. So in rectangle, again, ABCD, side AB must be equal to the opposite side DC. But AB is 3, therefore the opposite side DC must be also equal to 4 units in its length. Likewise, according to the symbol, in the same rectangle ABCD, side AD must be equal to the opposite side BC. But AD is x plus 1, therefore the opposite side DC must be also equal to x plus 1 units in its length. The next step we did a construction, that is to say from point D we draw perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point T and BC. This point is point M. By doing this construction, we get a polygonal ABME. Inside polygonal ABME, we have 1, 2, 3 others, and therefore this 4 piece here must be equal to 90 degrees in size. So inside polygonal ABME, we have 4 others, and therefore we can relate to polygonal ABME is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle ABME, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 3 units in its length. We define EM as h, so EM equals to h equals to 3. In the next step, we focus on the right upper triangle AEB. In the right upper triangle AEB, we define this angle as theta. So in the right upper triangle AEB, triangle theta equals to AB over AE. Again, tan theta equals to AB over AE. AB is 3, AE is 1. So in total, tan theta equals to 3 over 1, that is 3. Again, according to equation 1, tan theta equals to 3. We have the trigonometric identity that says that tan 45 degrees plus theta equals to 1 plus tan theta or 1 minus tan theta. We define the trigonometric identity as equation 2. We already found out that tan theta equals to 3, so we can solve the tan theta here by 3. We did it, and we found out that tan 45 degrees plus theta equals to 1 plus 3 over 1 minus 3. 1 plus 3 is 4, 1 minus 3 is minus 2, so 4 minus 2 is minus 2. So in total, as we found out that according to equation 2, tan 45 degrees plus theta equals to minus 2. But according to equation 1, we only found out that tan theta equals to 3. In the next step, we focus on the here AD is one side of rectangle ABCD, therefore AD is an absolute straight line. So if we focus on the right side of the straight line AD at point D, here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles from one side of a straight line is equal to 180 degrees. So which means we have the right side of the straight line AD at point D, we have this angle that is theta plus 45 degrees plus the missing angle DC in total must be equal to 180 degrees according to all three. Again, if we focus on the right side of the straight line AD at point D, the sum of the angles must be equal to 180 degrees. This is to say theta plus 45 degrees plus the third missing angle, DEC in total must be equal to 180 degrees according to all three. Here we subtracted theta plus 45 degrees inside, and we subtracted theta plus 45 degrees from this equation. And finally found out that the missing angle DEC equals to 180 degrees minus theta plus 45 degrees. This is the missing angle DEC is equal to 180 degrees minus theta plus 45 degrees. In the next step, we focus on this right lower triangle EDC. The right lower triangle EDC times 180 degrees minus theta plus 45 degrees equals to DC over ED. And again, in the right lower triangle EDC times 180 degrees minus theta plus 45 degrees equals to DC over ED. DC is 3, ED is x. So in total, times 180 degrees minus theta plus 45 degrees equals to 3 over x. And again, times 123 times 180 degrees minus theta plus 45 degrees equals to 3 over x. We have the trigonometric identity that says that times 180 degrees minus theta equals to minus times theta. So we can, according to this trigonometric identity, we get that tangent 180 degrees minus theta plus 45 degrees equals to minus tangent theta plus 45 degrees. Therefore, we can substitute tangent 180 degrees minus theta plus 45 degrees in this equation 3 by minus tangent theta plus 45 degrees. We did it, and if we found out that minus tangent theta plus 45 degrees equals to 3 over x. According to equation 2, tangent theta plus 45 degrees equals to minus 2. So we can solve the tangent theta plus 45 degrees in this equation 3 by minus 2. We have another minus, so I put the other minus here. So in this side of the equation 3 we have minus 2, that is plus 2 equals to 3 over x. And 2 equals to 3 over x. Here we multiplied this equation by x and finally found out that 2x equals to 3. Here we divided this equation by 2 and finally found out that x equals to 3 halves. 3 halves is 1.5. So now that it is equals to x is equals to 1.5 minutes in itself. Our test is to find out the area of this green shape. The green shape is the green triangle ABC. Again, the green shape is the green triangle ABC. Therefore, our test is to find out the area of the green triangle ABC. The area of the triangle equals to the base of the triangle times the height over 2. We choose the base as BC, the height is h, and we divide it by 2. The base is BC, the height is h over 2. BC is x plus 1, h is 3. Again, BC is x plus 1, h is 3 divided by 2. So the area of the green shape equals to x plus 1 times 3 over 2. But we only found out that x equals to 1.5. Therefore, x plus 1 is 1.5 plus 1, that is 2.5. times 3 over 2. 2.5 times 3 is 7.5, and 7.5 over 2 is 3.75 squared inside. So in both methods, we should know that the error that we're looking for in this version, that is the error of this ratio, equals to 3.75 squared inside. So we finish with the first question. In the next step, I'll repeat on the solution of the second question. In the second question, our test was to find out the radius of this semicircle that is described by this rectangle ABCD. QB equals to 1, PD equals to 2. Again, our test is to find out the radius of this semicircle that is described by this rectangle ABCD. First of all, ABCD is a rectangle, therefore all those four angles are right angles. We define the point of tendency of tangent DC with this semicircle, this point is point T. We define the point of tendency of tangent AD with this semicircle, this point is point P. Actually, we define the point of tendency of tangent BC with this semicircle, this point is point L. We define the center of this semicircle, this point is point O, and we define the radius of this semicircle as X. The next step, we join points O and T together by straight line. Point O is the center of this semicircle, point T is the point of the semicircle itself, therefore OT is the radius of the semicircle, this is equal to X. The radius of OT is equals to X, the radius of OT is drawn to point T, that is the point of tendency of DC with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius TO. If this is perpendicular to TO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and L together by straight line. OL is the radius of this semicircle, and it equals to X. The radius of L is equal to X, the radius of L is drawn to point L, that is the point of tendency of tangent BC with this semicircle. Whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to the sum rule, rule 1. So by doing those constructions, we get the lower quadrilateral OLCT. Inside the lower quadrilateral OLCT, we have 1, 2, 3 angles. Therefore, this surface area must be equal to 90 degrees inside. So in quadrilateral OLCT, we have 4 angles, and therefore we relate to quadrilateral OLCT is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OLCT, side OL must be equal to the opposite side CT. But OL is X, therefore the opposite side CT must be also equal to X when it's inside. Likewise, according to the sum rule, in the sum rectangle OLCT, side OT must be equal to the opposite side NC. But OT is X, therefore the opposite side NC must be also equal to X and it's inside. So we should know that quadrilateral OLCT is not a rectangle, but a square, why? Because of the fact that all of its sides are equal to each other. Each side equals to X. In the next step, we did a construction that is to show from point O, we go perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB, this point is point M. By doing this construction, we consider the upper quadrilateral MB LO. Inside the upper quadrilateral MB LO, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees inside. So in quadrilateral MB LO, we have 4 angles, and therefore we can relate to quadrilateral MB LO as a rectangle. But we also know that the opposite sides of the rectangle are equal to each other. So in rectangle MB LO, side OL must be equal to the opposite side MB. But OL is X, therefore the opposite side MB must be also equal to X and its length. What is the length of line segment MQ? MQ equals to MB minus QB. So MQ equals to MB minus QB. MQ equals to MB is X minus QB, this is 1. So total MQ equals to X minus 1 units in its length. The next step we did another construction, that is to say from point O, we go perpendicular on AD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AD. This point is point S. When doing this construction, we can do quadrilateral AMOS. Inside quadrilateral AMOS, we have 1, 2, 3 right angles, and therefore this fourth angle, as we got to 90 degrees inside, and therefore quadrilateral AMOS, we have 4 right angles, and therefore can relate to quadrilateral AMOS as a right angle. When doing this construction, we created another quadrilateral OSDT. So inside quadrilateral OSDT, we have 1, 2, 3 right angles, and therefore this fourth angle, as we got to 90 degrees inside. So in quadrilateral OSDT, we have 4 right angles, and therefore can relate quadrilateral OSDT as a right angle. But you also know that the opposite sides of right angle are equal to each other. So the lower right angle OSDT, side OT must be equal to the opposite side SD. Not OT is X, therefore the opposite side SD must be also equal to X in its length. What is the length of this line side SB? SB equals to SD minus PD. SD equals to SD, SB equals to SD, this is X minus PD, this is 2. So in total, SB equals to X minus 2 in its length. This is the big angle SOL. Is equal to 180 degrees plus 180 degrees. 90 degrees plus 90 degrees, it is 180 degrees. Again, the big angle SOL equals to 180 degrees inside, and we know that any angle that is equal to 180 degrees inside, it is defined as a straight line. Therefore, SOL is a straight line. If SOL is a straight line, then SL is also a straight line. Okay? So if SL is a straight line, then shape ABLS has 4 sides in total. 1, 2, 3, 4. Therefore, shape ABLS is a quadrilateral because it has 4 sides. So in quadrilateral ABLS, we have 1, 2, 3, 4 right angles. Therefore, quadrilateral ABLS is a rectangle. But you also know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABLS, side AB is parallel to the opposite side SL. So we can also have here a transversal QP that cuts those two parallels at those 2 points, Q and O. So all the requirements of Rule 10 are satisfied, and therefore can implement here Rule 10. I think we can Rule 10. According to Rule 10, corresponding angles between parallels are equal to each other. In the drawing, we have line A, this is parallel to line B. The red line C is defined as transversal. That is to say, it cuts those 2 parallels at those 2 points. Those 2 angles, the above defined as corresponding angles, and they are located between the parallels A and B, therefore they must be equal to each other and their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to this rule of 10. Likewise, those 2 angles, they are both defined as corresponding angles, and they are located between the same parallels A and B, therefore they must be equal to each other and their sizes. So if you define the size, this angle is better, then the size of this angle must be also equal to better, because they are equal to each other according to this rule of 10. So we can implement rule 10 in our drawing, as I already mentioned before. In the drawing we have side AB is parallel to the opposite side SL. QP is transversal. This is to say, it cuts those 2 parallels and points Q and O. So all the requirements of Rule 10 are satisfied, and therefore can implement here Rule 10. According to Rule 10, those 2 angles are both defined as corresponding angles, and they are located between the parallels A, B, and SL, therefore they must be equal to each other and their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to Rule 10. So in the upper green triangle MQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in a triangle. Likewise, in the lower right green triangle SOP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha, according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. OP is the radius of the OQ is the radius of the semicircle is equal to x. Likewise, again, OP is the radius of the semicircle is equal to x. Likewise, OQ is also the radius of the semicircle is equal to x. The next step prove that those two right angles can go into each other according to angle side angle rule. So why those two right angles can go into each other? First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two sides are both equal to x, therefore they are equal to each other. That is to say they are both the area of the semicircle is equal to x and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if we prove that those two right angles can go into each other according to angle side angle rule. That is to say, we prove that those two angles and the side that is included between those two angles is the side OQ, and this green upper right triangle MOQ corresponds equal to those two angles, and the side that is included between those two angles is the side OP, this green right lower triangle and OSP. Therefore, those two green right triangles can go into each other according to angle side angle rule. From the fact that they can go into each other, we derive that their corresponding sides are equal to each other. That is to say, MQ is equal to the corresponding side SO. MQ equals to SO. But we already found out that MQ equals to x minus 1. So we can write here that MQ equals to x minus 1. And from this equation, x minus 1 equals to MQ equals to SO. We derive that OS must be also equal to x minus 1 units in incident. This is side OS is equal to x minus 1 units in incident. In the next step, we implemented the Pythagoras theorem on this right lower green triangle OSP. According to the Pythagoras theorem, this green right lower triangle OSP, OP squared, that is the square of the hypotenuse, equals to OS square plus SP square. Repeat again, this green right triangle OSP, according to the Pythagoras theorem, the following equation is to OP squared, that is the square of the hypotenuse, equals to OS square plus SP square. OP is x, therefore OP square is x square, and it equals to SO square. SO is x minus 1, therefore SO square is x minus 1 square, plus SP square. SP is x minus 2, therefore SP square is x minus 2 square. So today we found out that x square equals to x minus 1 square plus x minus 2 square. We open the brackets of this side of this equation, we should found out that x square equals to x minus 1 square. X minus 1 square equals to x square, plus 1 square is 1, minus 2 times x times 2, minus 2 times x times 1 is minus 2x, plus x minus 2 square. X minus 2 square equals to x square, plus 2 square, that is 4, minus 2 times x times 2, that is minus 4x. We have x square on both sides of this equation, so x square gets cancelled. After we cancel x square on this side of the equation, we have nothing, that is to say 0, and on the other side of the equation, we have 1 plus 4, that is 5, minus 2x minus 4x is minus 6x, plus x squared. So now we should know that x squared on 6x plus 5 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus 4 to b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say x squared minus 6x plus 5 equals to 0. The variable that we are looking for is x, and x is the radius of this semicircle. The coefficient a equals to 1, the coefficient b equals to minus 6, and the coefficient c equals to 5. The only thing that we have to do is just to put the data of our specific quadratic equation inside this general formula for x, and this way we find out the value of the value of x. What x might have two solutions, and x is the radius of the semicircle. So actually we did it, and actually found out that x, that is the radius of the semicircle, equals to minus b. B is minus 6, therefore minus b is minus 6, that is plus 6, plus minus 4 to b squared. B is minus 6, so b squared is minus 6 squared, that is 36, minus 4 times a times c. So this is minus 4 times a is also minus 4 times 1 is minus 4 times c. C is 5, so minus 4 times 5 is minus 20. So inside root we have 36 minus 20 over 2a. A is minus 2a is 2 times 1, that is 2. So total we found out that x equals to 6 plus minus, and 36 plus 20 is 16, or to the square root of 16 is 4, so in total we found out that x equals to 6 plus minus 4 over 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to 6 plus 4 over 2. 6 plus 4 is 10 and 10 over 2 is 5. So if you found out that the radius of this symmetry, x equals to 5 units in its length. We have another solution for x. The second solution for x is as follows. X equals to 6 minus 4 over 2. 6 minus 4 is 2 and 2 over 2 is 1. So according to the second solution for x, the radius of this symmetry, x equals to 1 unit in its length. But x can never be equal to 1 because of the fact that SP equals to x minus 2. Again, SP was found out that last time SP equals to x minus 2 units in its length. So if x equals to 1, then x minus 2 is 1 minus 2, that's minus 1. But SP is a left, SP is a left must be a positive number, so due to the convolution, we must conclude that x can never be equal to 1. I gave you another reason that x can never be equal to 1, because of the fact that, again, SP equals to x minus 2. SP is a length, so SP is a length, it must be a positive number. What is a positive number? It is a number that's greater than 0. That is to say x minus 2 must be greater than 0. We added 2 to this inequality and found out that x must be greater than 2. If x must be greater than 2, x can never be equal to 1, that is less than 2. So due to the convolution, we must conclude that x can never be equal to 1. So I gave you two reasons that x can never be equal to 1. So the only solution to this question is that x, that is the radius of this semicircle, that is the radius that we're looking for this question, is equal to 5 units in its length. Okay, thank you very much.